Hello, Historical Geology. Here today, we are going to talk about environments of deposition. But first, I wanted to start by reviewing some concepts from a previous lecture whereby we spoke of relative time and stratigraphy. So looking on the screen, you are more than familiar with the geologic timetable, and you'll remember that first was invented as described by relative time. So looking at a sequence of layers, which now you understand is called stratigraphy. So when we look at the organization of rocks as a field of our science, it's called stratigraphy. And additionally, when we now look at the geologic timescale from oldest to youngest, you know that's called the law of superposition. So just to review, we've talked about the Precambrian time. That's the largest geologic unit of time at 80% of all geologic time. It's broken down into the Archean and Proterozoic from 4.6 billion years to 570 million years. We can look at the three different geologic eras, the Paleozoic, the Mesozoic, and the Cenozoic. We said that those are broken apart by mass extinction. Mass extinction, you will remember, is defined by at least 75% of all life on the planet dies instantly. So there was a mass extinction at the end of the Paleozoic and also at the end of the Mesozoic. We have broken up those different geologic eras into geologic periods, and we said that there was a mnemonic for that. So we use come over someday, maybe play poker, 3 jacks can take queen, and that's a way for you to organize the geologic periods. And then we said that some of the geologic periods specific to the tertiary and quaternary are broken up into smaller units called geologic epochs. And for the first test, you will not have to know the geologic epochs, but just realize that epochs are broken up into periods of climate change. So distinct units of climate change. And because those units are so close to the surface, they're 66.4 million years to present day, we have a good understanding of what that climate change can look like because there's so much geologic record present for us to study. So familiarity with the geologic time scale, and I also want you to recall stratigraphic correlation. So we've already said the law of superposition, and that means that when we look at strata, or which is another word for rocks or rock units or rock layers, we say they're organized from oldest to youngest. So your youngest surface is exposed at the surface. And when we look at geologic maps, they are mapping the surface exposure. So in and around Rome, Georgia, as an example, the rocks are about 300 million years old. When we look at the other principles of stratigraphy, we say that rocks were originally laid horizontally. So they're originally flat when they're deposited. So whether that is sediment falling onto a beach environment, or if we think of the dissipation of calcite in the bottom of the ocean to form limestone, they're always going to be originally horizontal. So when we look in the natural environment and we see things that are tilted or folded, then something has happened after they were deposited to cause them to change. And then the next is lateral continuity. So again, when rocks are first formed, they're laterally continuous, and then something happens in their environment to cause disruption. So we commonly talk about the erosive power of river systems. So if you stand on a river bank on the right and you look across to the left, you can assume that that area was laterally continuous. It is the force of the water that caused the carving of a channel. And those are principles founded by Nicholas Steno in the 1600s, and he is considered to be the father of stratigraphy. In addition to those three principles that Charles Lyell wrote about in the very first geology book published in 1865, The Principles of Geology, there's two other ones that he added. So he added the idea of cross-cutting relationships. And so when you have a rock unit, it can be intruded by a body of magma. And those are called dikes or sills. when we refer to them as igneous structures. And so you have that body or mantle plume. When you have that body of magma that works its way up through a crack or crevice into previous existing rock, the magma is going to be younger than the rocks around it. And additionally, there is the principle of inclusion, and that means when the body of magma works its way up into those rocks, it can sometimes erode the rocks and include them as pieces into the formation. Those are referred to as xenoliths, and the inclusions are older than the magma intrusion itself because they formed first. So that's just a little bit of a review, and I wanted to do that because today we're going to focus on environments of deposition, and this is one of my true loves when we talk about sedimentary rocks. So in order to get started, I want us, since we have now a foundation also about sedimentary rocks, I want to think about what the story is that they can actually tell us. So you'll remember when we talked about sedimentary rocks, we said that they can be either clastic, bioclastic, or chemical or evaporate. So clastic is one that is going to be formed by the breakdown of sediment, and we used sandstone as an example of that, or shale. We talked about bioclastic. So bioclastic means that it's organic, so it's made of something that was once living. And oftentimes we can talk about the sedimentary rock called limestone. And so there's limestone that is fossiliferous, where you can clearly identify the fossils, or the matrix is made out of calcium alone from things that were once living, corals, clams, shells, etc. So you have limestone and this bioclastic, and then you also have coal. So we said coal is made out of pure carbon, and it forms in areas where there's an abundance of vegetation. And then we talked about things that were chemically formed or evaporate formed. But important to today's lecture, and really as we move on thinking in terms of the fossil record, we need to know how these rocks in and of themselves, even without a fossil record to tie them to, tell us something about past environments. So when we think of sandstone, we are going to think of that in terms of forming in a beach environment. And that makes sense, right? So we looked at the samples of sand, and what can happen is the sand is exposed at the Earth's surface, and it can have rain. Rain contains minerals, so it contains calcium and magnesium naturally. And so you can end up with that water falling onto the surface of that sandstone if it's undisturbed, and that will act as a cement. So it will cement those grains together, and then over time, those sand grains will get compacted or lithified together. And that's how sandstone forms. So we can think in terms of sandstone representing a beach environment, or even like a river environment, or even a desert environment. But let's, for the present time, think in terms of a piece of sandstone representing a beach environment. Limestone, then, if we move away from the beach and you're thinking in terms of being in that shallow marine environment, so you're playing in the swash zone, and you're thinking about all the shells that you're collecting, right, on a beautiful sunny day in Panama City. When you're doing that, you are witnessing the development of limestone. So those shells, if they lithify together, that will become something called coquina, and we saw that in laboratory. But also it can form a sedimentary type of rock called limestone. And so we've looked at those examples of limestone that react to acid because they're calcium rich. Calcium is what those shells are made of. And we've even looked at examples where the limestone still contains the remnants of those shells, right? So a piece of limestone then is deposited or formed in a shallow marine environment. Are you picking up what I'm throwing down, right? So we've started at the beach. We've moved our way into a shallow marine environment where limestone is being formed. And then we can go out into the deep abyss where you're deep sea fishing, and that's where shale is being formed. So shale sometimes is very black and contains a lot of organic material that's mixed in with the very, very fine pieces of clay-sized particles. So you're imagining a river that's coming from on land offshore, and as it's doing that, it's carrying those very fine particles of shale. And so shale represents a deep marine environment. And so that makes sense too if we want to think about oil and gas recovery, like if we're interested in that as a non-renewable natural resource. Shale often contains oil, and so that's why, like, if you're in areas of maybe Mississippi, if you're like by Biloxi, you can see the offshore drilling that's taking place. They're drilling into those deep shale layers because that's going to eventually contain organic material, and that organic material is going to decompose into oil and natural gas. And then we can think about coal, which is another form of bioclastic sedimentary type of rock, and that represents a wetland environment. So now, without knowing anything else, anytime that you're in the environment and you find a piece of sandstone in place, what you're trying to envision is that sometime in the past, that was a beach. Get your mind around that. So when you're walking up to the House of Dreams and you're looking at sandstone in outcrop, you're envisioning the past environment, the ancient environment, the paleo environment being a beach environment. And when you see a piece of limestone, that represents a shallower marine environment, and the shale represents a deep marine environment. So without knowing anything else, you are now able to interpret what the past environments used to look like. And then even relatively, and then later we'll talk about how we assign absolute ages to these rocks. So here's a definition that I want you to write in your notes, and it's a definition of a cyclothem. It's a hefty definition. A vertical rock unit consisting of a series of rock beds that represent changes in the environment. What does that mean? A vertical rock unit consisting of a series of rock beds that represent changes in the environment, sea level fluctuations, climate conditions, etc. So get that into your notes and digest that idea. So let's think about it. Okay, so what we have on the screen is I put a picture of an outcrop. So you're imagining that a sandstone layer is on the bottom, a limestone layer caps that, and on top of that limestone layer is the shale unit. So you've got a layer of sandstone, a layer of limestone, and then on top you have a layer of shale. And what you know by the law of superposition, that the sandstone is the oldest unit and the shale is the youngest unit because they're organized in sequence of relative time. So when we're thinking about this, we're also thinking in terms of how that environment is changing over time. So you're moving from a beach environment to a shallow marine environment to a deep marine environment. And we know that because we're using the environments of deposition to act as a clue or a proxy to give us a picture of what those past environments must have looked like. And again, like the present is a key to the past is a key to the present. So we can look at the modern day beach environment and understand how sandstone, limestone, and shale are formed. So the cool thing about a cyclothem is that if you look at this package of sedimentary types of rocks, you can tell how the past climate has changed right before your eyes. Because what? It went from a beach environment to a shallow marine environment to a deep marine environment. So that means, what is the sea level doing? At that location, at that time, it was getting deeper. The sea level was getting deeper over geologic time. And we can go back and we can age date those to figure out that. So if we truly want to know something about past climate change, we can look for the sedimentary rock record to give us an indicator of that, because we could figure out how quickly those environments change, how deep the water became, and we can make those estimates. So the cool thing is that we can look at that in reverse too. So if I give you an example where the bottom unit is shale, and above that shale is limestone, and then on the top is sandstone, and I ask you the question, what is sea level doing in this condition? You would say sea level is decreasing over time. Sea level is decreasing over time. So my question then to you is to think about, well, what would cause sea level to increase and what would cause sea level to decrease? So I think sea level increases is understandable, right? So anytime that you have temperatures that are increasing, we see this on the planet today, right? You have an increase in sea level rise because you have an increase in glacial melt. And so that's called a hothouse. You'll see that term time and time again when we start to explore the geologic record. Opposite of that is a cold house. So if you're going from shale to limestone to sandstone, where your sea level is decreasing, that probably means your glaciers are growing. So I think that's just so cool, because this is something that you can even do as you're exploring throughout the world and looking at these different rocks and just looking how those packages of rocks have changed over time. Okay, so we can look at rocks vertically, and when we do that, that's called a cyclothem, and we said that cyclothems can have periodicity, so you can see these packages of change over time. Then we can also look at these laterally, so we can look for lateral change. So you can look for vertical change, and then you can look for lateral change. So when we do that, that's called a facies, and I give you another definition. Significantly different rock types occupying laterally distinct parts of the same geologic time. So to repeat, significantly different rock types occupying laterally distinct parts of the same geologic time is a facies. And the question I put on the screen is deposition occurring at the same time in each environment? So that's the bigger question. And then you're looking at the coastline of Myrtle Beach here on the right. And so, so what you see is your beach environment representing your sandstone. You see the swash environment representing limestone, and then some distance offshore is your deep marine environment. Is the deposition occurring at the same time? Well, sure it is. And so you can look for them in a lateral sequence, moving from sandstone to limestone to shale, just as you can in the geologic record. So you have lateral environments, and you can look for changes vertically as well. And so lateral changes are important because it gives us another tool to identify the changes in sea level. So when we do this, we can talk in terms of a transgressive and a regressive boundary. So a transgressive boundary is block A on this diagram, and this represents a time when you have advancement of sea over the land. So you're essentially saying that sea level is getting higher. And so you're imagining a shift in your lateral facies. This is also called a high stand. And when we meet in class, I'm going to draw some of these diagrams on the board. But you're thinking in terms of lateral deposition. So if you have an increase in sea level on land, you're going to encroach on top of your beach environment. So where your beach was is now going to be your shallow marine environment. Oppositely, when your sea level decreases, you end up with a regressive facies. So sea level is decreasing, and so now you have more exposure of your beach environment. Your beach environment gets larger, and that's because your limestone environment, your shallow marine environment, is moving farther offshore. So it's a process of mapping laterally. And so when you think in terms of a geologic map, and you're looking at the ages of rock exposed at the Earth's surface, you're also looking for lateral changes from one location to the other. And these can be quite large scale, as you can imagine. So a transgressive facies then represents a high stand. And so that's going to represent a hothouse condition. So a time when sea level is rising. And then your regressive facies is going to represent a period of time when the climate is getting colder. So a period of glaciation, also referred to as a cold house, because that water is now being trapped up in the glacial ice. Okay, so we're going to put this all together in a package that's referred to as Walther's Law. And I've got to meet good old Walther, spent some time with him when this theory just came out. So Walther Law, by definition, the identification of vertical and lateral changes in sedimentary rocks reflect how past environments shift positions through time. And I think you understand that now, right? So these individual rock units that are sedimentary give us clues as to how the environment is changing. So we can apply that to something that's called the worldwide sea level curve, and that's what's on the screen. So Walther's Law identifies the worldwide sea level curve. And let me tell you how he did this. So, because it looks very simple on the screen, doesn't it, when we look at Walther's Law? So it is based on geologic time, right? Oldest to youngest. The Vendian was referred to as a glacial period. You don't have to know that, just to understand that it was during the Precambrian. And you notice that our geologic time starts at 600 million years old. So before the end of the Precambrian unit, essentially. So oldest to youngest. And what Walther did is he looked at cyclothems and he looked at lateral facies, and he was identifying transgressive and regressive boundaries throughout the world. So he was looking at coastlines, and he was looking at the rock record and trying to establish what, over geologic time, the sea level had been doing. And he was able to synthesize this into a global sea level curve. Also on the screen, you will notice at the bottom, there's an arrow. And at the top, there's an arrow. And that represents the present day sea level. So what you're noticing by looking at Walther's Law is that Walther's Law is either increasing or decreasing relative to what sea level is today. So it's either lower to the right or higher to the left. And this is a relative sea level for the entire globe. And so what's fascinating is that Walther's Law is telling you if the world was in a transgressive or regressive boundary, that is, if it was in a hot house or a cold house. So I'm going to give you a second to look at this graph. And my question for you is, when was a period of a hot house? And when was a period of a cold house? Are you looking at the graph? There's a couple. So overall, the period of highest sea level on the planet was during the Ordovician. The Ordovician really through the Silurian. And what you notice from looking at the graph is that during the Ordovician, sea level was more than 400 meters greater than what it is today. 400 meters greater than today. So if we want to put that into feet, it's about 1,200 feet higher than what it is today. And that's really important when we start to talk about the uprising of life in the Ordovician, because as you can suspect, the entire world was covered in water. Like there was hardly any, if all, landmass that was above sea level. So if we're thinking in terms of the fossil record and what was living on the planet, you're looking for sea-dwelling creatures. And that's exactly what we find. You'll notice that there is a steady decrease of sea level pretty much from the Silurian all the way to the Triassic, the end of the Triassic. And we'll talk about that. That's going to have to relate to a Pangea cycle, so a supercontinent cycle. And then, so that would be at the end of the Triassic, or about 200 million years ago, that would be your cold stand. So a period of time when the globe goes to a glacial phase. And so sea levels are going to decrease, and that's also going to be influenced by the coming together of the Pangea. And then sea level begins to increase. So when we look at modern day sea level, it's moderate compared to what the high stand it used to be. And this is kind of indicative because when we think of climate change in terms of geology, and we can do that quite confidently by looking at ice cores and sediment cores, we suspect that we actually should be in a glacial phase. And that kind of makes sense when you look at the synchronicity of this diagram. And glacial cycles do have periodicity, and that's called the Milankovitch cycle, which we'll get into later. So Walther's law, it looks like a very simple graph, but just realize like so much data went into this, and it's a fantastic tool for us to set the foundation of trying to explain the geologic record, the uprising of life, and how that is impacted by climate. Look for Walther's law on your first exam, for sure. Okay, so I want to wrap up with just realizing that there's other environments of deposition. So we really simplified it. And the reason why I did that is because Walther was just looking for transgressive and regressive boundaries based on the cyclothems, sandstone, limestone, and shale. So he's looking for those particular packages. But what I want you to realize is that there's many different environments of deposition. And it's truly the idea that the present is the key to the past. So if you see it happening at modern day at the Earth's surface, imagine that those signatures can also be trapped in the rock record, and we can look for those. Perhaps they're less common, right? So on this diagram here, it starts up at glaciers. I've got a slide that's going to tease out glaciers a little bit more, but you can understand that you can have mountainous areas, and off those mountainous areas, you end up with river systems that flow into the ocean ultimately. And so anytime we have a river environment, that's called a fluvial environment. So river environments are called fluvial environments. Rivers end at deltas. So we can think in terms of the Mississippi Delta, right? And so these are massive areas where sediment is deposited into a body of water. So the Mississippi River starts all the way up in Minnesota, where its headwaters start, so where it originates, and it flows the length of the United States and deposits it at the Mississippi Delta. So right there in Louisiana. And that's called a deltaic system. So when we talk about like the source of clay-sized particles to produce shale, that's where it's coming from. So it's coming from all the way from Minnesota. You've got boulder-sized particles, and then they eventually break down, and then they end up in the delta as very fine particulate. You have your beach environments. You have your tidal shore environments. You can see your evaporite deposits. Lacustrine means lake. So a lacustrine deposit is a lake deposit. Aeolian AEOLIAN, is any time that you have a sedimentary rock that's formed by wind. So you're thinking about dunes, and dune systems are aeolian. They're wind-generated systems. Coral reefs. And the other thing I want to point out on this is anytime that you have a passive margin, also called a divergent plate boundary, and we're going to tease this out a little bit when we talk about Pangea. You move from your continental coast to the continental shelf, and the point where before you fall down a slope is called the continental margin. So you have the continental crust or your beach environment, you have the shelf, and that's where your limestone is formed, and then you have the slope. So the slope goes down into the deep abyssal plain. So oftentimes if you're deep sea fishing, you're trying to get past the slope, and that's where you catch like the really big fish. And that distance depends on where you're at along the shoreline. And then to break down coastlines a little bit better into environments of deposition, and you may have visited the Georgia coastline, or there's barrier islands really all the way up through North Carolina. There's 13 different barrier islands in the state of Georgia. And this is showing you tidal flats, a lagoon environment. Lagoons typically are, it depends on their size. They can be freshwater, but sometimes they're brackish. So they can have some salinity. And the reason why they can have some salinity is because although the barrier islands is protecting them from the ocean, you usually have these inlets. And the areas where you have these inlets are called the tidal delta. So barrier islands are not meant to be static. They're really meant to be dynamic systems. We have since tried to control these with jetties and different types of barricades and land structures to try to keep them in place. But they're really meant to be dynamic systems that are really always changing. And they certainly change with or without our discretion during hurricane and big storm events. So there's a good picture on the right to illustrate what this actually looks like, and I think the schematic helps you. So lagoon types environments are either shallow freshwater or shallow brackish, typically calm. And so when we look at the geologic record, those are still like limestone deposits, but usually what happens is because it is such a quiet environment, the fossil record is fantastic. So you don't get the destruction of the shells because they're protected from the major wave systems. And I just want to show you a picture of glacial environments. Glaciers obviously are near and dear to my heart since writing my textbook. And I hope that you get to see a glacier sometime in your lifetime, because they're just fantastic dynamic systems that hold a whole lot of energy. So the picture on the right shows what's called an outlet of a glacier. This is a valley glacier. So what usually happens is you have a major ice sheet, and then the ice sheet wants to move down gradient because they have energy. And so as they're moving down and from high energy to low energy, they're scouring the bedrock underneath it. And so they're creating these perfect U-shaped valleys. And so the diagram on the very bottom left-hand corner shows you an area where the glacier has melted. And that's kind of like the beauty, because even if the ice melts, you still end up with these remnant features that tell you about the past glaciation. So when we talk about the last glacial maximum, 14,000 years ago, Ohio was covered in 2 kilometers worth of ice. Well, how do we know that? We know that because we can look for these past geologic features, and we can look at the rock record, and it gives us a clue as to those past environments. So you look for U-shaped valleys, and as these glaciers are moving down gradient, they're incorporating the bedrock into the glacier, and they're going to They are going to deposit it laterally. So those are called lateral moraines. That's what you're seeing on this picture. So you're seeing those ridges. Those are called lateral moraines. And then at the toe of the glacier, so where the glacier has stopped moving, that is called a terminal moraine. And the terminal moraine usually contains something that's called glacial till or glacial flour. And it is just this very, very fine sediment that is formed by the movement and the scouring of that basement material. And so that is deposited at the toe of the glacier. And also boulders, depends on the size and scope of the outlet glacier, but boulders, cobbles, etc. are combined in that. So those are just some more common environments of deposition. We're going to look at this in laboratory. It's one of my very favorite labs because it really gives you a clue as to what has happened and transpired in the 4.6 billion years of our planet. So I am going to stop here today. Take care. Have a great day. See you later.